Good morning, class. We are Group 7. I am Shuangjing, and I will represent our group to talk about how to measure contact angle of nanoparticles. Why is it important to measure contact angle of nanoparticles? Particles at interface can interact differently with two faces due to asymmetric positioning. This is reflected by the contact angle. The mechanical properties and friction coefficient of the interface with nanoparticles are greatly affected by contact angle. Due to difficulty of measuring contact angle of nanoparticles, most studies assume a constant contact angle, usually 90 degrees. When the actual contact angle is smaller than 60 degrees or greater than 120 degrees, it becomes strongly dependent on line tension. In the worst case, the particles may detach from the interface due to line tension. In this presentation, we will talk about 5 techniques to measure contact angle of nanoparticles at fluid interfaces. The first technique we introduce is gel trapping technique. GTT is usually combined with AFM to determine the contact angle of particles at air-water or oil-water interfaces. Here are the steps to apply GTT. First, nanoparticles are spread at the interface. Then, put gellant in the aqueous phase to trap the adsorbed nanoparticles without changing interfacial energy and contact angle. After that, remove the top phase, cure with silicone, usually PDMS, to obtain a replica of the nanoparticle monolayer. Peel it off and wash with hot EDTA and water. After drying the replica, using tapping mode AFM to measure the vertical protrusion and the radius of the particle. The contact angle can be calculated accordingly. The equation shows the relationship between contact angle and particle radius r at protrusion height h. Note that r and h are both average values. This equation is valid for both hydrophilic and hydrophobic interfaces, as shown in the figure on the upper right. In this experimental setup, the calculated line tension is about 10 to the minus 12 to 10 to the minus 11 Newton, and it is negligible. Here are the advantages of using GTT with AFM. It is possible to automatically determine the average contact angle of many nanoparticles using proper microrobots and software. GTT with AFM can image the self-assembly process of nanoparticles at fluid interfaces, which cannot be achieved by other techniques, including direct AFM imaging. It can determine the contact angle of the smallest nanoparticle so far in use, which is 37 nanometers. In the future, this method can measure even smaller particles. Despite the advantages of GTT, it is not applicable to certain types of interfaces, such as water hexane. In addition, its accuracy is affected by surface charge density. Fresca, or freeze fracture shadow casting, is an alternative technique to GTT. It is combined with cryo-SEM to measure the nanoparticle contact angle. Cryo means icy cold. The figure illustrates the process of applying Fresca. Initially, particle monolayer is frozen at the fluid interface. Then the interface is fractured with the immobilized particles so that a solid sample is obtained. Then the sample is coated with metal at an oblique angle alpha. After metal evaporation, a shadow is created and ready for SEM observation. The figures above show the nanoparticles at the frozen interface after metal evaporation. The left figure shows the hydrophilic case, and the right shows the hydrophobic case. The difference is that in hydrophilic case, particle is immersed in ice, and radius r cannot be directly measured, so instead shadow length k is measured for calculation. In hydrophobic case, the particle equator is above the frozen interface, and radius is easy to measure. Projected height L should be measured for both cases, and the shadowing angle alpha is already known. The equations for calculating contact angle of hydrophobic and hydrophilic nanoparticles are shown. Plug in the measured parameters R, K, L, and the known shadowing angle alpha. You will get the contact angle. The advantages of Fresca are summarized below. It can measure contact angle of particles as small as 10 nanometers. It is applicable to more types of systems, such as interfaces that GTT cannot analyze. Accuracy of the measurements is increased because average analysis can be performed on the large regions of monolayer. It can detect inhomogeneous variability of particles at the monolayer. Our next technique is called excluded area formalism. It is based on the idea that the surface can only be occupied by one component. When nanoparticles are added to a monolayer of insoluble surfactant, they create an area shift, as shown in the lower right figure. As the silica particles with different contact angles are added to the interface, the excluded area is shifted to different degrees. As the equation shows, this area shift is dependent on the number of nanoparticles at the interface, the particle radius, and contact angle. The excluded area formalism is applicable to both hydrophobic and hydrophilic particles in a wide range of sizes, and it is good for particles adsorbed irreversibly. The limitations of excluded area formalism are listed below. It is difficult to know exactly the number of particles at the interface. It is only valid when there is no interaction between particles and the surfactant molecules. Contact angle is dependent on surface tension, and it is necessary to measure area shifts under low surface pressures to minimize the effect of surface tension. If you remember the gas lecture on optical properties characterization, you should be able to recall that ellipsometry is very sensitive to surface conditions. It can resolve the thickness that is much smaller than wavelengths of light. The nanoparticle monolayer at the air-water interface can be considered as a bilayer, with the upper layer composed with particles and air, and the lower layer consisting of particles and water. Ellipsometry is used to measure the reflected amplitude of polarization and phase shift to find the thickness of the upper layer. The equation on the lower right shows the relationship between contact angle and thickness of the upper layer with known particle diameter. Ellipsometry has much higher resolution than normal reflectometry. The limitation of ellipsometry is mainly due to its model dependence. It assumes that the upper layer and lower layers can be viewed as different media with the same index of refraction and ignores any light scattering by particles. Film caliper method is a technique by forming a sufficiently stable particle bridge in a liquid film. In the lower left figure, it is shown that at some film thickness h equals He, the surface free energy is minimized and the liquid film does not deform even after particle adsorption. The interference pattern in an optical microscope is used to determine this unique thickness of the liquid film. With known particle diameter d and measured liquid film thickness He, the contact angle can be calculated by this equation. FCM can determine the contact angle of many particles simultaneously, improving accuracy and efficiency. It can also measure variability of non-spherical particles. It has a significant limitation that it can only determine the contact angle of hydrophilic particles at air-water interface. Although we introduced 5 techniques to measure contact angle of nanoparticles, there are still some scientific gaps in this area of research. There is little research on correlation between particle interaction and contact angle. However, long-range dipolar interactions can sometimes be significant. There are so many variables involved in the measurement of contact angle. Discrepancies in measurement may arise due to different assumptions made in these techniques or limitations of methodologies themselves. Non-spherical particles have unique properties and became interest of recent research, but there is little research on how to measure their contact angle. Based on these scientific gaps, we suggest that future research should focus on correlating particle interaction and contact angle, establishing a standard protocol to evaluate contact angle, and extending current knowledge of spherical particles to study contact angle of non-spherical particles at fluid interfaces. In this presentation, all the 5 techniques covered are related to the first set of topics, surface, interfaces, and nanostructures of the class. They are all related to the concept of contact angle and hydrophobicity. Excluded area formalism involves using surfactant at the interface and reading pressure area isotherm. The area shift is related to the parking area that was covered in Dr. Moldgill's lecture. The key to understand film caliper method is to realize that a surface free energy minimum is achieved when film thickness equals to He. Ellipsometry was covered in the gas lecture in optical properties characterization. The important concepts are resolution, amplitude, and phase shift, which are used to calculate thickness of the upper layer. That's all we have. Thank you for watching.